Okay, take your seats. Let's get started. Last class before spring break. I'll try to make it short so you can get started on spring break early. So I'm going to do two things today. I'm going to wrap up our discussion of scaling. And what I cover today is going to be especially important because Project 3, which will be handed out the day after you return from spring break, builds on the ideas here. So it uses what we have discussed already plus the ideas here. And then I'll just go over the midterm exam, give you some summary about how you all did. And for those of you who are here in person, I have your answer books, which I can give back to you. For everybody else, they can get it after spring break. Okay? So we covered conceptually how to do scaling. And what I want to do is to walk you through an example. And this example is exactly what you will do in Project 3. So if you were to create a small website today, you'd create a bunch of HTML files in your local file system. You might have a .htaccess file there to give some kind of permissions. You can have some CGI scripts that let you have some level of executable content, right? Pretty simple, straightforward web stuff. And then you'd pick an open source web server, put it in front, and you're done. This works. That's all it takes. All of you can do this easily. So the question is, that design works. You have 5 users, 10 users. But once you start being really successful, it starts getting to be a little tricky. Adding more content is trivial. As long as you have disk space, you can throw more stuff in it. That part is easy. Adding more users might be a little trickier. Manipulating htaccess, etc., starts getting tricky. Most importantly, the machine on which you're running has finite CPU capacity. Now, it may vary. Some of those machines may have 16 cores or 32 cores. Some of them may have lots of memory. But eventually, there comes a point, and that point may be at 20 users, might be at 100 users, somewhere, you're going to start seeing very slow response time. The question is, how do you scale this system? Basically, this is the curve, right? Everything I've taught you in queuing theory, remember that one slide, the iron law of queuing theory, this is capturing this picture. That early in the game, things look pretty tame, no worries. And then all of a sudden, as you get close to the knee of this curve, things start getting very bad very quickly. And once you're up here, life is miserable. So the question is, how do you make sure that your system always is operating in this portion rather than getting beyond the knee? Okay? So one simple starting point would be to say stuff like htaccess, it all starts, it's pretty difficult to manage. Much nicer to use a real database, to have user accounts, and they might even have different privileges as to what they can do on this website. It gets much more flexible and rich control of the content. So that's easy. This results very quickly in splitting that single Apache web server into 2 stages. You have a front end, that is the web server, same web server, but there's a separate back end which deals with the storage and the database. So this is the picture that you get with that. You pick something like MySQL. MySQL is where you would put structured data. So for example, people with user accounts, the information regarding what the permissions are that they can use. Maybe things related to money, payments, subscription fees, right? All that stuff you'd put in databases. And then there's what is called unstructured content. JPEG images, MP4 movies, right? The system doesn't look inside them. They're just a big bag of bits. And for that kind of unstructured data, some kind of AFS or AFS-like distributed file system fits perfectly. So even if I have multiple front ends, you're going to see in the next slide, the fact that you're using a distributed file system means all of them have access to the same data. And how close the implementation of this distributed file system is to one-copy semantics determines how easy the system is to use in this application. Typically, open-close, one-copy semantics, exactly like you have learned in class, typically works very well. If reads are much more dominant than writes, then callback-based approaches work extremely well. Okay, so this is a good starting point to make the system scalable. And this Apache web server, is not any different from before. It's using a slightly different backend structure. And it is possible that this takes you quite far in scaling. Maybe it takes you to hundreds of users, maybe even a few thousand. Okay? Very quickly, what starts to happen in these kinds of systems is that when you begin, very often, most of your content is static content. Once your website starts attracting more users, it becomes very tempting to augment your revenue by using those people as targets of advertising. And once you go down that path, you've already learned from our discussion about caching versus marking data as uncacheable, that you need to start using dynamically generated content rather than statically generated content, right? So the dynamically generated content might have advertising customized to the user built in. The same New York Times article. Come back. The same New York Times article, when delivered to person A over there, has one kind of advertisement. Delivered to person B over here, there's a different kind of advertisement. And the database here, MySQL, might contain information about the habits of these users based on learning from their recent accesses. So very quickly, the need to do dynamic content generation starts becoming a performance bottleneck. When all you had was simple static files, or you had simple files from AFS, that's not much processing that I need to do. It involves reading from the disk and then transmitting over TCP, HTTP to the client. I mean, that's all there is to it. Yes?
For the dynamic content, how we use the GDN we talked about a couple of classes ago?
By the time you get to CDNs, you've already scaled far beyond everything I'm talking about. Okay? Using CDNs is not cheap. We are still here. Okay? So this is in the gap in between. So somehow the addition of dynamic content, again driven by, for example, advertising, means that the simple front end is not adequate. We somehow have to add more processing capability at this end. So what you do is to introduce a middle tier called an application server, whose sole job is to use the storage backend, AFS and or MySQL or some other database, use it and in a possibly user-specific way, combine it to create an HTML page. By the time that HTML page is constructed, things like advertising, etc., have already been embedded into it. And then that HTML page can be handled by the Apache web server. Okay? So now you have the old backend, same as before. I've drawn it a little differently here, but it's the same thing. Notice when it comes to AFS or some other distributed file system, I can have multiple machines because they can all be caching sites for the same static content. Notice, however, that MySQL is only running on one machine. I'll say more about that in a second. The fact that there are multiple machines here, but only one there, is not an accident of drawing. It's real. This application server is how you scale up generation of dynamic content. Okay, and so in the open source world, things like Tomcat, in the closed source world, IBM WebSphere is an example of an application server. So this has become, another product in the distributed system space. The output of this is HTML, files which have everything bound into them that gets handed to this content server whose job it is to deliver it. Okay, so far so good. Now, if you keep increasing further, eventually, even though that front end is not doing very much, it's being given HTML pages, it's creating lots and lots of TCP connections, over which it's using HTTP for each user. Finally, that becomes a bottleneck. And so what you do is you clone these and you use a front-end load balancer to direct you to the right web server. Now, the details about this load balancer are actually quite subtle. In the best case, all of these are identical. Okay? In which case, a really trivial algorithm like randomly directing an incoming request to any one of these will work fine most of the time. But the real world is a little trickier. Think, for example, if you are visiting a website and at some point you hit the back button. When I go back to the previous page, most use cases expect an identical page to what I saw the last time. If I randomly pick handling of that back request, then that may not be so easy to achieve. Because the first time I visited that page, the HTML was constructed for me, customized. It had the pictures of the spring break destinations for me that make me drool, which are different from what makes you drool. And when I hit the back button, I need to be shown that particular one. Right? And if I pick randomly, who knows which one I'll be shown. So The only way you can do this is to make the load balancer be much more sophisticated. It has to have some knowledge that this is Will over there, who has just started a brand new session of surfing the web. For the duration of this session, however you define session, okay, it's a bit tricky with HTTP. What is a session? You don't have the equivalent of open, close, right? There's no such thing. All you have are individual HTTP requests. You could use some detail like inter-arrival time between HTTP requests. Anytime the gap is longer than, say, pick some number, 15 minutes. That's a big, huge number. We say that second session is a new session. But if the inter-arrival time is some smaller value, yes, it's still part of the previous session. So now the load balance has to be smart enough to first see, am I dealing with a new user? And things like cookies are the easiest way to do this, right? Because they're integrated into each of the requests. And then if it is a new session, then you pick the random assignment and you have a table of, Will has been assigned this server. And, Jerry at the back there has been assigned that second server. I don't see Ashley today, but if she were surfing, she would be assigned the third server, and so on, right? And when a user has not sent any HTTP requests for a while, you can imagine deleting him from the table. So the next request that comes from that person will be considered the beginning of a new session, and a new assignment can be made. Okay, so there are many, many heuristic approaches to achieve the effect of what I described to you. So now hitting the back button and seeing exactly the same page becomes feasible because you're dealing with the same static content server. So when I hit the back button, it is a request for the same static HTML page that I saw a few seconds ago. I don't have to go back and reconstruct a brand new page, etc. Of course, the semantics of the web service may say, I'm sorry, when you hit the back button, we basically log you out automatically. The implementation can do that if it wishes, because it doesn't want people to use the back button. That's a system design choice that you have. Any questions so far about this picture? Yeah?
The load balancer was looking to store some space from the client to the other side. Like this kind of short memory on which server is going to use that.
It doesn't need to know much. So if there's a cookie, some mapping of the cookie to small integer will do. That's good enough. Or you could use the entire cookie, but cookies are big and painful, so usually try to do some simple hashing of that to some small integer, and that's all. Yeah. Yeah.
So we are not talking about caching there, right? Because when you hit the back button, the page will already.
This thing is caching. It depends on how you think about it. The app server constructs a simple HTML page from dynamic content. It doesn't remember it. It is this static content server which has that locally. It's not really a cache because that is the only existing copy of that HTML file. It was constructed for you and is written to disk. So it's not a cache of some master copy somewhere.
So the client doesn't store that created HTML file on its own.
Say this again. The client doesn't do what?
Does not cache the HTML file.
I don't know what the client is welcome to do caching. Most likely, in these systems, the HTML page that is constructed will have the uncacheable bit marked. But of course, you can hack your browser, okay, to ignore uncacheable, in which case you will keep using the same information. Your browser can choose to use the TTL field, and if none is specified, to pick one of its own. Right? It's not forced to honor the uncacheable bit. But all we know is if from the same user a request for the same page is received by this front end, via this load balancer, first of all, it'll be directed to the same server. And on that server, it sees that there's already an HTML page cached. Oh, cached is the wrong word, already present. And it hands that back. Right? So technically, it depends on how you use the term caching. Up to now, we have used the term caching to mean data caching. This is a more generalized concept called result caching. Right? In compilers, the term used is called memoization, long word, because people like to sound smart. Okay? It is result caching. You do a computation once, you save the result. In this case, the computation was all the hard work that the app server did. It went to the database, it got JPEG images from the distributed file system, it looked up the database to see your advertising preferences. It did a lot of work, right? And then it constructed this beautiful, mouth-watering HTML page and gave it to this guy. And that page is present locally, which is what you see. Okay? Good question. Any other questions? All right. Simple so far. Now this database turns out to be a big problem. Distributed file systems like AFS, you throw more clients, as long as the workloads are biased towards reads, it'll work. At open-close semantics, it's single writer, multiple reader, works fine. And so the portion of this system that is the most difficult to scale always is the database. And the reason is you only use the database when nothing else works. It is the place in which you put stuff that A, has to be persistent, B, there's no debate. It has to have one copy semantics at very fine granularity. So the implementation of this database is like your project one. You send SQL commands to the database, it executes them. There's no caching anywhere. There's caching inside the memory. That's purely in the implementation of the database. In terms of caching of results from the database, it's not done in the system. So this turns out to be a really, really difficult component to scale out. People have in the past created distributed databases, but attempts to scale out the database function have never been satisfactory. Almost always, if you in the areas where they are successful, you look at the data carefully, and there's no reason it should have been in the database. You could have put it in AFS. So it's only the really bad stuff that's difficult to cache, that's difficult to replicate. Only those portions of the data are typically in the database. And by definition, the only way to improve performance is not to use scale out, but to use scale up. So some years ago, you may recall Oracle, which is one of the most successful database companies, purchased Sun Microsystems. Why did they do that? It turns out they purchased it for one tiny portion of Sun Microsystems. And that portion was a class of hardware specifically designed to scale up database performance. That's the only thing they wanted. All right? They didn't care about Java. They didn't care about the Lustre file system, all the workstation stuff. They didn't care about all of which they sold all the pieces of, retaining only this one portion which they use for scaling up. So in your web server system, there's one portion of it, which is the database for which you use scale up, and then all the other components use scale out. And that model works typically very well. Okay? And so I think I've covered all of this. So the one other performance improvement you can do is, even for a database, reads are much more frequent than writes. So if you're shopping at Amazon, most of the content of a web page is constructed from static information, like this clothing you're thinking of buying, or this gadget for your kitchen you're thinking of buying. Well, the manufacturer's picture, the description, all of that is, it changes once every 6 months, not on a daily basis. But how many items are left in stock changes every second. So that portion of it would be in the database. The rest of the information would be in the file system. And it's the application server that would construct that web page so that when you look at it, it's one web page. In addition, knowing your previous browsing history, that page has special stuff meant to attract you. Just you. Okay? So if you feel unloved, websites can make you feel very happy. They seem to know all about you. They track your behavior. They pay attention to you. Questions?
What is the specific reason for database cannot be scaled horizontally? Let's say we have multiple database and then we use hash.
So there are simple ideas you can use. You can do things like all products whose SKU, which is some number that uniquely identifies that product. You can imagine if the first digit or the last digit, right, whichever, is 0, you use that server. If it's 1, you use this server. So some kind of very simple hashing kind of approach can be done. So you can split up the space that way. But that's static. It's not dynamic. If just today, because COVID was detected and everybody wants masks, right? They're all going to hit the same server. True scale-out would allow runtime load balancing, whereas what I described to you is static, right? Over there in that corner, something else, like swimsuits, are the queue length is 0, but nobody's traveling, right? So nobody wants that. The queue length, you can't load balance across resources, whereas true scale-out, it's completely dynamically determined. Right? So that's what it is you can't do. So you can use these kind of strategies to use multiple machines, but they're static approaches. Another approach to make it semi-static, but at the cost of a lot of storage, would be to replicate all the data on all the servers' disks, and then dynamically, so in theory, one of these could service all of the requests. However, at runtime, you change the sharding dynamically. You say, for the next 15 minutes, that server over there is going to handle hash values 0, 1, and 2. This server is going to handle hash value 3, because empirically, in the past 15 minutes, somehow, I don't understand why, this seems to be in demand, and so on, right? And you can change that. The reason you can change it is because the dynamic information that has to be exchanged is quite small. Maybe if you now say, for the next 15 minutes over there, that's only going to handle hash value 0. This one is going to handle 1, 2, and 3. There may be some data I now have to synchronize, because how many widgets of things with hash values 2 and 3 are left? That is only known current in that. My copy is a stale copy of that. So you might need to do at the point of reallocation, might have to do more work, but it's possible. But these are all nowhere as good as the true cloud-native, glorious approach, which says, scale out, don't worry, there's very little work you have to do. Right. Do people see the difference between the two? Right? Why the simpler and easier it is to horizontally scale out, the closer you are to pure cloud native. Okay. As I mentioned to you, even databases very often have extremely high read to write ratios. It is true that, say, on an airline, on a given flight, how many seats are left, which seats are taken, right? That's dynamic information. That's the right place for that is the database. But if you look at a given user, that user is going to look at flight A, think about it. Nah, it takes too long. The layover is too long in Newark or Houston or somewhere. Let me find another flight. I look at something else, right? So there are a lot of read accesses to the database. Eventually, this person picks something and purchases the ticket, and they're right operations. But if you looked at this user's behavior, the reads, even to the database, dominated. So what has turned out to be extremely valuable is a in-memory cache and also a generalization of things that can be put in in-memory caches called key-value stores, which are abstractions in which you don't really know what the bits mean. It's a bit like file systems, except instead of having a path name like home, Satya, something, or AFS, Andrew, course 15440, right? You just have some big fat hash string. Right? That's it. Other than that, a key value store is quite similar to a file system. So key thing about in-memory databases is if a crash occurs, everything in it vanishes. It's non-volatile. That's why it's giving you performance. So the resulting system looks like this. You have a load balancer, and how sophisticated this load balancer is depends on what your system does. I just explained this to you. You have scaled out web servers here. You have scaled out application servers. You have scaled out distributed file system. You have scaled out memcache. And you have one scaled up, not scaled out, database. Right? This design is kind of the classic web server design in modern systems. And almost every one of them fits this picture quite well. Any questions about this? Okay. That's the end of scaling. We are done. And as I've told you, Project 3, which we'll hand out right after spring break, will be on this. So all I have left is the midterm exam. So let me give you a few comments, and then I'll go over the answers to the questions. Most of you did very well. This was an easy exam. There were 189 of you. The mean and the median were both very good, 85, 86. This is good. There have been years in which it has been much lower. So we were gentle with you. Or you are very smart. You can interpret the data either way. Nobody got 100, but one person came close. And so overall, very good. Would it be helpful to all of you if I went over the answers very briefly, just to make synchronize? Okay.